Welcome to the Sleep and Learn channel. We invite you to listen to interesting scientific facts that will help you fall asleep gently and, at the same time, learn something new. Relax, close your eyes, and let a calm voice guide you into the world of knowledge and sweet sleep. The gentle architecture of our solar system. The solar system is not a chaotic place, even though it may appear vast and wild. In reality, it is a carefully balanced cosmic neighborhood, moving in quiet harmony around a single steady star, the Sun. About 4.6 billion years ago, our solar system began as a calm, rotating cloud of gas and dust. Over time, gravity gently pulled this material together, forming the Sun at the center. Around it, smaller clumps slowly gathered into planets, moons, asteroids, and comets. What may seem dramatic in scale unfolded over millions of years, a slow, patient process shaped by gravity and time. The Sun contains more than 99% of all the mass in the solar system. Its steady light and warmth create the conditions that allow planets to orbit in predictable paths. Each planet follows an elliptical orbit, like a calm track drawn in space. These orbits rarely change, and their rhythm has remained stable for billions of years. The four inner planets, Mercury, Venus, Earth, and Mars, are rocky and compact. Beyond them lies the asteroid belt, a quiet region filled with ancient fragments that never became a planet. Farther out are the gas giants, Jupiter and Saturn, followed by the icy giants, Uranus and Neptune. Even farther still lies a distant realm of icy bodies known as the Kuiper Belt. Despite their differences, all these objects share a common motion. They orbit the Sun in the same general direction. Most also rotate in that same direction, like dancers in a slow cosmic waltz. The solar system is often described in terms of distance. Light from the Sun takes about 8 minutes to reach Earth. That means when we feel sunlight on our skin, we are experiencing energy that left the Sun 8 minutes ago. A small but peaceful reminder of the scale of space. Yet even across these enormous distances, the solar system remains gravitationally connected. The pull of the Sun keeps planets in their paths. Jupiter's gravity helps shield inner planets from many wandering comets. Moons circle their planets with steady devotion. Everything moves, but nothing rushes. If we could step back and observe it from afar, the solar system would not look frantic. It would appear slow and deliberate, a system built not on noise, but on balance. And in that balance, there is something deeply relaxing. The quiet heart of our solar system, the Sun. At the center of our solar system rests a star of steady brilliance, the Sun. Though it appears small in the sky, it is vast beyond easy imagination. If the Sun were hollow, more than 1 million Earths could fit inside it. And yet, from our distance of 150 million kilometers, it feels gentle, a warm presence rising each morning without fail. The Sun is a nearly perfect sphere of glowing plasma. Deep within its core, hydrogen atoms slowly fuse into helium. This process, called nuclear fusion, releases extraordinary amounts of energy. But the energy does not rush outward. It can take thousands, even hundreds of thousands of years for energy created in the core to reach the surface. What finally leaves the Sun as sunlight has already taken a long, patient journey. When that light departs the surface, it travels through space at incredible speed, about 300,000 kilometers per second. Yet even then, it needs 8 minutes to reach Earth. Every sunrise is slightly delayed light from the past. The Sun accounts for more than 99% of the solar system's total mass. Its gravity gently anchors the planets, guiding their orbits with consistency. Without the Sun's steady pull, the planets would drift into deep space. Instead, they move in predictable paths, held in balance by this luminous center. Despite its powerful interior, the Sun behaves with remarkable stability. It shines with almost constant brightness over long periods of time. This steadiness is one reason life has been able to flourish on Earth. A slightly brighter or dimmer star might have created a very different world. The surface of the Sun, called the photosphere, glows at about 5,500 degrees Celsius. Above it lies the corona, an outer atmosphere so hot and delicate that it extends millions of kilometers into space. During a total solar eclipse, the corona becomes visible as a soft, ghostly halo surrounding the darkened Sun. It is one of the most peaceful and awe-inspiring sights in astronomy. The Sun also breathes outward in a gentle stream known as the solar wind. This continuous flow of charged particles travels far beyond the outer planets, shaping a vast bubble around our solar system called the heliosphere. Within this protective region, our planetary family moves together through the Milky Way. Though the Sun will continue shining for about 5 billion more years, it is currently in a calm, middle-aged stage of its life. It is neither young nor near its end. It simply continues, steady, constant, reliable. If we imagine the solar system as a quiet home, the Sun is its hearth, glowing, central, life-giving. It does not shout or flicker wildly. It radiates, and every planet, every moon, every small drifting comet responds to its quiet gravity. The inner worlds: Mercury, Venus, Earth, and Mars. As we drift outward from the steady warmth of the Sun, we encounter the inner planets, 4 small, rocky worlds shaped by heat, time, and gravity. These planets are often called the terrestrial planets, meaning Earth-like, because they share solid surfaces and dense cores. Closest to the Sun is Mercury, a quiet and airless world. Its surface is marked with countless craters, reminders of ancient impacts from long ago. Mercury experiences extreme changes in temperature. During its long daylight, the surface can become intensely hot, while at night it grows deeply cold. And yet, Mercury follows its path around the Sun with remarkable precision, completing one orbit every 88 Earth days, swift and steady in its rhythm. Next comes Venus, often called Earth's twin because of its similar size. But Venus is wrapped in thick clouds of carbon dioxide that trap heat in a powerful greenhouse effect. Beneath its bright cloud cover lies a world of volcanic plains and immense pressure. Venus rotates very slowly and in the opposite direction of most planets. A single day on Venus lasts longer than its year. Despite its harsh surface conditions, from space it appears calm, a pale golden sphere glowing softly in the sunlight. Then we arrive at Earth, our home. Earth is the only known planet with liquid water oceans on its surface. Its atmosphere gently scatters sunlight, creating blue skies and soft sunsets. The Moon orbits faithfully nearby, stabilizing Earth's tilt and contributing to the steady rhythm of tides. Earth's orbit lies within the Sun's habitable zone, where temperatures allow water to remain liquid, a delicate balance that has supported life for billions of years. Beyond Earth lies Mars, often called the Red Planet. Its rusty color comes from iron oxide dust covering its surface. Mars has towering volcanoes and vast canyons, including Olympus Mons, the largest volcano in the solar system. Though today Mars is cold and dry, evidence suggests it once had flowing water long ago. Gentle dust storms now sweep across its plains, reshaping the surface slowly over time. These 4 worlds share similarities, yet each expresses its own quiet personality. All formed from the same early cloud of dust and gas. All orbit the same Sun. But distance and atmospheric differences have shaped them in unique ways. Between Mars and the next region of the solar system lies the asteroid belt, a broad band of rocky remnants that never formed into a planet. These fragments are ancient, preserving clues about the early days of planetary formation. They drift peacefully, following predictable paths around the Sun. The inner solar system is not empty space. It is a region filled with motion, history, and subtle balance. Each orbit, each rotation, continues without hurry. The majestic giants, Jupiter and Saturn. As we travel beyond the quiet belt of asteroids, the solar system begins to feel vast in a new way. The rocky worlds give way to giants, immense planets composed mostly of gas, swirling storms, and deep atmospheres. Here we meet Jupiter and Saturn, the largest planets in our cosmic family. Jupiter is the largest planet in the solar system. More than twice as massive as all the other planets combined, it dominates the outer region with gentle authority. Though it has no solid surface like Earth, Jupiter's thick atmosphere is layered with bands of clouds that circle the planet in soft stripes of cream, orange, and brown. Within these clouds lies the Great Red Spot, a massive storm that has been swirling for over 3 centuries. It is large enough to swallow Earth whole, yet from a distance, it appears almost like a calm brushstroke on a painted sphere. Jupiter rotates quickly, completing one day in less than 10 hours. This rapid spin shapes its clouds into elegant horizontal bands. Jupiter also acts as a quiet guardian of the inner solar system. Its enormous gravity attracts many comets and asteroids, reducing the number that travel toward the inner planets. In this way, Jupiter has likely played a role in protecting Earth over billions of years. Orbiting Jupiter is a remarkable family of moons. Among them are 4 large worlds discovered by Galileo in 1610: Io, Europa, Ganymede, and Callisto. Each is unique. Europa hides a vast ocean beneath its icy crust. Ganymede is the largest moon in the solar system, even larger than the planet Mercury. These moons move in harmonious patterns around Jupiter, forming a miniature solar system of their own. Farther outward lies Saturn, known for its magnificent ring system. Saturn's rings are made of countless particles of ice and rock, ranging in size from tiny grains to mountain-sized fragments. Though they appear solid from afar, the rings are delicate and thin, like cosmic lace encircling the planet. Saturn itself is composed mainly of hydrogen and helium, similar to Jupiter, but it is less dense. In fact, Saturn is so light for its size that, in theory, it could float in an enormous ocean of water. Its atmosphere features soft golden tones and subtle storms that drift quietly through its upper layers. Saturn also has many moons, including Titan, a world with thick clouds and rivers of liquid methane flowing across its surface. Titan's calm, hazy appearance makes it one of the most intriguing bodies in the solar system. These giant planets remind us of scale. They are immense, yet they move with quiet consistency. Their gravity shapes the paths of smaller objects. Their moons orbit faithfully. Their storms swirl, sometimes for centuries. In the outer solar system, distance grows, light softens, and motion slows into a deeper rhythm. And beyond these giants lie even more distant worlds, colder, bluer, and quieter still. In the next part, we will journey to the icy realms of Uranus and Neptune, where sunlight becomes faint and the solar system fades gently into darkness. The distant blue realms, Uranus, Neptune, and the edge of the solar system. Beyond the golden glow of Saturn, sunlight grows softer. Distances stretch wider. The warmth of the sun becomes faint, and the solar system enters a quieter, colder region. Here we find Uranus and Neptune, the icy giants, distant, blue, and serene. Uranus is unique among the planets. It rotates on its side, tilted at an angle of about 98 degrees. Instead of spinning upright like Earth, Uranus rolls along its orbit. This unusual tilt creates extreme seasons. For many years at a time, one pole faces the sun continuously, while the other remains in long darkness. Yet, despite this strange orientation, Uranus moves calmly and predictably in its wide orbit, taking 84 Earth years to complete one journey around the sun. Its color is a soft blue-green, caused by methane in its atmosphere, absorbing red light and reflecting blue. Beneath its upper clouds lies a deep and cold interior, composed of water, ammonia, and methane ices. Though powerful winds move through its atmosphere, from afar, Uranus appears smooth and tranquil, almost like a quiet marble suspended in darkness. Even farther from the Sun lies Neptune, the most distant major planet. Neptune shines a deeper blue than Uranus, its color rich and luminous. Though it receives only a small fraction of the sunlight that Earth does, Neptune is surprisingly dynamic. It holds the fastest winds in the solar system, racing through its atmosphere at tremendous speeds. And yet, from a distant viewpoint, Neptune appears peaceful, a calm blue sphere slowly circling the Sun once every 165 Earth years. Neptune also hosts a system of moons. The largest, Triton, orbits in the opposite direction of Neptune's rotation, a sign that it may have once been a wandering object captured by Neptune's gravity long ago. Triton's icy surface reflects faint sunlight, glowing softly at the edge of our planetary neighborhood. Beyond Neptune lies the Kuiper Belt, a broad ring of icy bodies left over from the early solar system. These objects are small and distant, moving slowly in the cold outer darkness. Among them are dwarf planets such as Pluto, once considered the ninth planet. Pluto follows an elongated orbit that sometimes brings it closer to the Sun than Neptune, though their paths never collide. Farther still stretches the scattered disk, and, beyond that, the distant Oort cloud, a vast spherical shell of icy fragments that may extend halfway to the nearest stars. These regions are rarely disturbed. Objects there may take thousands or even millions of years to complete a single orbit around the Sun. At this outer boundary, the Sun's influence gradually fades. Its solar wind forms a protective bubble known as the heliosphere. Beyond this boundary lies interstellar space, the quiet realm between stars. The outer solar system feels distant and hushed. Light is dimmer, movement is slower, time stretches longer. And yet, even here, gravity maintains its gentle order. Every world, every fragment of ice, continues its patient orbit around the same steady star. A quiet system in motion. Our place among the stars. When we step back and imagine the solar system as a whole, it becomes something gentle and harmonious. A family of worlds bound together by gravity, light, and time. From the warm brilliance of the Sun to the dim icy bodies at the edge of interstellar space, everything moves in quiet coordination. The planets do not wander randomly. Each follows a precise orbit shaped by gravity. These paths are not rigid lines, but graceful ellipses, maintained by the delicate balance between motion and attraction. The same force that draws an apple toward Earth keeps Neptune circling billions of kilometers away. The solar system itself is not standing still. It travels around the center of the Milky Way Galaxy at a speed of about 220 kilometers per second. Yet, even at this tremendous velocity, the motion is smooth and steady. One complete orbit around the galaxy takes roughly 230 million Earth years, a galactic year. Since the time of the dinosaurs, the solar system has moved only a small portion along this vast journey. All the planets orbit in nearly the same plane, like coins spinning on a flat table. This shared alignment reflects their common origin in the ancient rotating cloud of gas and dust. Even today, that early harmony remains visible in their orderly motion. Small bodies continue to drift quietly among the planets. Comets trace long, graceful arcs, sometimes returning after centuries. Meteoroids occasionally enter Earth's atmosphere, briefly lighting the sky as shooting stars. These are gentle reminders that the solar system is dynamic, yet rarely chaotic. There is also an invisible structure holding it together: gravity. It is not loud or visible, but it shapes every orbit and every rotation. Without gravity's steady influence, there would be no predictable sunrise, no seasons, no tides. From Earth, we often look outward with curiosity, sending spacecraft across millions and even billions of kilometers. These missions move slowly, taking years to reach distant planets. And yet, compared to the age of the solar system, even decades are brief moments. In the vastness of space, our solar system is only one of countless planetary systems. Around distant stars, other worlds orbit quietly, following their own steady rhythms. What we observe here, balance, motion, and stability, may be common throughout the galaxy. And yet this system is also uniquely ours. Here, on a small blue planet orbiting an ordinary star, life has had time to grow and reflect. We exist within a structure shaped by gravity and illuminated by steady sunlight. We live in a place where the cosmic dance has remained stable long enough for oceans, forests, and consciousness to appear. When viewed from afar, the solar system is not noisy or frantic. It is patient. It is ordered. It is continuous. The sun will continue to shine for billions of years. The planets will continue their quiet revolutions. The outer icy bodies will drift in distant cold. And through it all, our solar system will remain what it has always been: a calm island of motion, traveling together through the stars. Time, silence, and the long future of our solar system. The solar system is not only a structure of space, it is also a story of time. Every orbit marks a year, every rotation marks a day, every slow revolution around the galaxy marks an age beyond ordinary imagination. On Earth, we measure time in seconds and seasons, but in the solar system, time stretches outward into millions and billions of years. Mercury completes an orbit in just 88 Earth days. Neptune takes 165 Earth years to circle the Sun once. And the Sun itself will continue shining for about 5 billion more years. A span so vast that all of recorded human history occupies only a thin fraction of a single moment. The Sun is currently in a stable phase of its life, quietly converting hydrogen into helium in its core. This stage, known as the main sequence, is one of balance. The outward pressure of fusion gently counters the inward pull of gravity. For billions of years, this equilibrium has held steady. But even stars evolve. Far in the future, when hydrogen in the Sun's core becomes scarce, it will slowly expand into a red giant. Its outer layers will stretch outward, reaching far beyond its current size. The inner planets will be transformed by this change. Eventually, the Sun will shed its outer layers, leaving behind a small, dense core known as a white dwarf, a faint ember of what was once a bright star. Yet this transformation is unimaginably distant. For now, the solar system remains in a long, quiet middle chapter. The planets will continue their orbits. The moons will circle faithfully. The icy bodies of the Kuiper belt will drift in cold darkness. Even small gravitational interactions between planets, subtle tugs over millions of years, unfold gradually, shaping orbits with gentle precision. The solar system also carries a record of its past. Ancient craters on Mercury and the Moon preserve the memory of early impacts. Meteorites that fall to Earth are fragments of primordial material, older than our planet itself. In their mineral structures, they carry the chemistry of the young solar system. Silence is one of the most profound features of space. Without air, sound does not travel between the planets. Storms may swirl on Jupiter and winds may race across Neptune, but the vast distances between worlds remain silent. Motion exists without noise. Even sunlight moves quietly. When we look at the night sky, we are seeing the solar system from within, orbiting a steady star surrounded by darkness and distant starlight. Our world is part of a long continuum, shaped by gravity and guided by time. The solar system has endured collisions, migrations, and changes in its earliest days. Now, it rests in a long era of stability. That stability has allowed life to emerge, to think, to observe. In this vast and patient system, we are both small and deeply connected. We live inside a structure that is older than mountains, older than oceans, older than life itself. And as it moves quietly through the Milky Way, the solar system continues its slow, elegant journey, not rushing, not pausing, simply unfolding across time. A small blue world in a vast, gentle universe. As we come to the end of our quiet journey, we return to a simple image: a small blue planet orbiting an ordinary star. From a distance, Earth is only a pale sphere of light, suspended in darkness. It is one world among many, moving in harmony within a vast and steady system. The solar system does not rush. It does not tremble in chaos. It turns. The sun rises and sets because Earth rotates with calm precision. The seasons change because our planet tilts gently as it circles its star. The moon glides across the night sky in predictable rhythm, guiding the tides. Even distant Neptune follows its path faithfully, though its year lasts longer than a human lifetime. All of this motion happens quietly. If we could step far beyond the outer planets and look back, we would see a faint golden glow marking the sun, surrounded by tiny points of reflected light, the planets. Beyond that, only the soft shimmer of distant stars. The solar system would appear peaceful, almost still, though it is always moving. There is comfort in this stability. For billions of years, gravity has held these worlds together. The same physical laws that shaped the earliest dust clouds continue to guide each orbit today. Nothing here is accidental or hurried. Everything follows the gentle mathematics of motion. And within this structure, life has emerged. On Earth, oceans rise and fall, forests grow, winds travel across continents. Human beings look up at the night sky and wonder. We send instruments beyond our planet, crossing millions of kilometers to photograph distant giants and icy moons. Through these efforts, we slowly come to understand the quiet order that surrounds us. The solar system teaches patience. Planets take years, even centuries, to complete their journeys. Comets return after long absences. Stars evolve over billions of years. In comparison, our own lives are brief, but they unfold within something ancient and enduring. When you look at the night sky, you are not seeing randomness. You are witnessing structure, a balanced system that has remained stable long enough for consciousness to arise and observe it. The sun will continue shining tomorrow. Earth will complete another rotation. The outer planets will drift along their immense paths, and the solar system will keep traveling around the Milky Way, quietly and without urgency. In this vast universe, we live within a place of remarkable harmony. A steady star, a family of worlds, a small blue planet where life can pause, breathe, and look upward. And perhaps that is the most relaxing fact of all. That glowing band is the Milky Way. For most of human history, people did not know what it was. They told stories about it. In ancient Greece, it was the spilled milk of a goddess. In China, it was the silver river separating star-crossed lovers. In many indigenous traditions, it was a celestial path for spirits. But tonight, we gently set aside myth, and we explore what it truly is. The Milky Way is not a cloud, not a mist, not a glowing stripe painted across the sky. It is an entire galaxy, a rotating gravitational city of stars, and we are inside it. That is the first calming truth. You are already traveling through space, right now. The Milky Way contains somewhere between 100 and 400 billion stars. Astronomers still debate the exact number because counting stars across such vast distances is incredibly difficult. To understand its size, imagine this. The galaxy stretches about 100,000 light-years across. A light-year is the distance light travels in 1 year, about 9.46 trillion kilometers. Light is the fastest thing in the universe. Yet even light takes 100,000 years to cross from one side of our galaxy to the other. Let that scale gently settle in your mind and breathe. The Milky Way is classified as a barred spiral galaxy. From above, it would look like a vast spiral pinwheel, with long, curved arms extending outward from a bright central bar. These spiral arms are not solid structures. They are more like cosmic traffic waves, regions where stars and gas are slightly more concentrated. Stars drift in and out of these arms over time. Nothing is rigid. Nothing is fixed. Everything flows. Our Sun lives in a small structure called the Orion Arm, sometimes called the Orion Spur. It is a minor arm, a kind of galactic side street, located between two larger arms known as the Perseus Arm and the Sagittarius Arm. We sit about 27,000 light-years from the galactic center, not too close to the crowded core, not too far out in the sparse outer edge, a comfortable middle region. And our entire solar system orbits the center of the galaxy at roughly 828,000 kilometers per hour. That sounds incredibly fast, but the galaxy is enormous. So one full orbit, called a galactic year, takes about 225 to 250 million Earth years. When dinosaurs roamed Earth, our solar system was in a completely different position around the Milky Way. Since humans evolved, we have not even completed a single orbit. You are riding a cosmic carousel so large that its motion feels perfectly still. Now imagine zooming upward, past Earth's atmosphere, past the Moon, beyond the orbit of Mars. The Sun becomes just another star, and eventually, even our solar system shrinks into a single faint point within one spiral arm. The spaces between stars are enormous. If the Sun were the size of a coin, the nearest star would be several kilometers away. Space is not crowded. It is mostly empty. And yet, that emptiness contains wonders. Between the stars drift vast clouds of hydrogen gas. These are called molecular clouds. Some are hundreds of light-years wide. They are cold, dark, quiet. But inside them, gravity slowly pulls material together. Over millions of years, clumps form. Pressure increases, temperatures rise, and eventually, nuclear fusion ignites. A new star is born. The Milky Way forms about 1 to 3 new stars every year. It may not sound like much, but over billions of years, that steady rhythm builds galaxies. Some stars are small red dwarfs. They burn slowly and can live for trillions of years. Others are massive blue giants, living fast and dying young. When very large stars exhaust their fuel, they explode in events called supernovae. These explosions are among the most energetic events in the universe. In a single moment, a supernova can outshine an entire galaxy. But supernovae are not only dramatic, they are creative. Inside those explosions, heavy elements form: carbon, oxygen, iron, calcium. The atoms in your bones, in your blood, in your breath, were forged in ancient stars. You are made of Milky Way material. You are not separate from this galaxy. You are part of its long chemical story. At the center of the Milky Way lies something extraordinary: a supermassive black hole known as Sagittarius A star. It has a mass about 4 million times that of our Sun. But it is not a cosmic vacuum cleaner. It does not suck the galaxy inward. Stars orbit it at safe distances, held in a stable gravitational balance. In 2022, astronomers captured the first direct image of this black hole's shadow, a glowing ring of hot gas surrounding a region where light itself cannot escape. Even black holes are part of the galaxy's quiet order. A glowing ring of hot gas surrounding a region where light itself cannot escape. Even black holes are part of the galaxy's quiet order. And the Milky Way does not exist alone. It belongs to a small collection of galaxies called the Local Group. The largest member is the Andromeda Galaxy. Andromeda is about 2.5 million light-years away. It is slowly moving toward us. In about 4 billion years, the Milky Way and Andromeda will begin a gentle gravitational dance. Over hundreds of millions of years, the two galaxies will merge. Stars will pass one another at vast distances. Direct collisions between stars are extremely unlikely. Space is too spacious. Even cosmic collisions are slow and graceful. And as you listen to this story, our galaxy continues to rotate. The Sun continues its orbit. Stars continue to be born. Some stars are ending their lives in quiet white dwarf fading. Others are collapsing into neutron stars. The Milky Way is dynamic, alive with motion. Yet from Earth, it appears calm, a soft, luminous band. A reminder that we are part of something vast and ancient. The galaxy formed about 13.6 billion years ago, shortly after the universe itself began. It has survived cosmic collisions, starburst phases, and gravitational tides. And tonight, it turns slowly above you. As your breathing deepens, remember this: you are riding a planet, orbiting a star inside a spiral arm within a galaxy, moving through a universe still expanding. And yet here you are, safe, still, listening. Let the scale of it soften your thoughts. Let the vastness quiet the noise of the day. The Milky Way does not hurry. It rotates patiently over hundreds of millions of years. And you, for this moment, can rest inside it. Take one more slow breath, in and out. The galaxy continues its quiet spin in the dark, and we will continue exploring it, very gently, in the next chapter. Take another slow breath in, and gently let it go. Imagine now that we are drifting inward, not toward Earth, not toward the Sun, but toward the very heart of our galaxy. The center of the Milky Way lies in the direction of the constellation Sagittarius. From Earth, it appears as a dense, glowing region in the sky, thick with stars, dusty, bright. But much of it is hidden from ordinary view. Clouds of interstellar dust block visible light, so for centuries, we could not clearly see what was happening there. Only in the 20th century, using radio telescopes and infrared observatories, did astronomers begin to uncover its secrets. The center of the Milky Way is about 27,000 light-years away from us, and it is busy. Stars there are packed far more densely than in our neighborhood. In our region of space, the nearest star beyond the Sun is about 4 light-years away. Near the galactic center, stars can be only a few light days apart. It is a crowded cosmic city. At the very core lies something extraordinary. A region no larger than our solar system, invisible, silent, but immensely powerful. This is Sagittarius A star, the supermassive black hole at the center of our galaxy. Its mass equals about 4 million suns. Yet, despite its enormous mass, it is surprisingly compact. If Sagittarius A star replaced our Sun, its event horizon would extend only out to about the orbit of Mercury. Black holes do not actively pull everything inward. They behave like any other object with mass. If our Sun were magically replaced by a black hole of the same mass, Earth would continue orbiting normally. Gravity depends on mass, not on whether something is a star or a black hole. Sagittarius A star influences only its immediate surroundings. Stars near it orbit at tremendous speeds, thousands of kilometers per second. Astronomers have tracked individual stars making full elliptical orbits around it. These measurements confirmed its mass with remarkable precision. And yet, the black hole is relatively quiet. It is not actively consuming large amounts of material. It glows faintly in radio waves. Compared to the brilliant, active galactic nuclei in distant galaxies, ours is calm, peaceful. Even at the center of the Milky Way, there is balance. Now let us slowly drift outward again, away from the galactic core, back into the spiral structure. The Milky Way's spiral arms are not fixed, solid limbs. They are density waves. Imagine traffic on a highway. Cars move forward, but sometimes a wave of congestion forms. The jam itself moves slowly, while individual cars enter and leave it. Spiral arms are similar. Stars orbit the galaxy at different speeds, depending on their distance from the center. But the spiral pattern persists as a gravitational wave moving through the disk. Gas clouds entering a spiral arm become compressed. Compression triggers star formation. That is why spiral arms glow brightly. They contain many young, hot, blue stars. These stars shine intensely, but they live short lives, only millions of years. Cosmically speaking, that is brief. Blue stars burn hot and fast. When they die, they explode as supernovae, enriching the surrounding gas with heavier elements. And so the spiral arms are places of renewal, continuous cycles of birth and transformation. Our Orion arm is modest in size, about 3,500 light-years wide, but it holds remarkable structures. One is the Orion Nebula, a vast star-forming region about 1,300 light-years from Earth. Inside it, hundreds of young stars are being born. Some are only a few 100,000 years old, astronomical infants. The nebula glows because ultraviolet light from newly formed stars excites the surrounding gas. Hydrogen emits a reddish glow. Oxygen emits greenish-blue light. Nebulae are among the most beautiful objects in the galaxy. They are stellar nurseries, gentle cosmic wombs. Now imagine zooming further outward. The Milky Way's disk is not infinitely thin. It has a thickness of about 1,000 light-years in the region of the Sun. Near the center, it bulges outward, forming the central bar. Beyond the visible disk lies something mysterious: the galactic halo. This halo contains older stars, globular clusters, and something far more elusive: dark matter. Dark matter does not emit light. It does not absorb light. We cannot see it directly, but we know it exists because of gravity. Stars in the outer parts of the Milky Way orbit faster than they should if only visible matter were present. The extra gravity must come from something unseen. Dark matter forms a vast spherical halo surrounding the galaxy. In fact, most of the Milky Way's mass is dark matter. The visible stars and gas are only a small fraction of the total. The galaxy you see in the night sky is just the luminous tip of a much larger structure. It is comforting in a way. The universe contains mysteries, and we are still discovering them. The Milky Way also contains about 150 known globular clusters. These are tightly packed spheres of ancient stars. Some are more than 12 billion years old. They formed early in the galaxy's history. Each globular cluster may contain hundreds of thousands of stars. They orbit far above and below the galactic plane, like ancient satellites circling their parent galaxy. Some astronomers believe that parts of the Milky Way were built by absorbing smaller galaxies. Over billions of years, our galaxy merged with dwarf galaxies. Their stars became part of the halo. Even today, we see streams of stars that once belonged to smaller galaxies. The Milky Way grows slowly through cosmic assimilation, and it will continue to evolve. Galaxies are not static. They breathe on billion-year timescales. Now let your mind settle into that rhythm. Stars forming, stars fading, gravity shaping vast structures. Everything moving, but nothing rushing. You're inside a galaxy 100,000 light-years across, orbiting a black hole 27,000 light-years away, surrounded by dark matter we cannot see. And yet, here you are, small, warm, conscious. The Milky Way has been turning for nearly the entire age of the universe. And tonight, as it continues its slow rotation, you can rest within it. No need to hurry across 100,000 light-years. No need to solve dark matter. Just breathe. Every star you see in the night sky is alive in its own way. Not alive like a tree or an animal, but alive in motion, in change, in transformation. Stars are not eternal. They are born, they evolve, and they eventually fade. Let us begin at the very beginning. Deep inside a cold molecular cloud, a vast region of hydrogen gas and cosmic dust, gravity quietly begins its work. These clouds are enormous. Some are hundreds of light-years across. They are dark because dust blocks visible light, but inside them, something gentle is happening. Tiny fluctuations in density cause certain regions to become slightly heavier than their surroundings. Gravity pulls more gas inward. The region grows denser. Colder gas collapses more easily, and the collapse accelerates. Over thousands, then millions of years, a clump forms. It begins to rotate slowly. As it contracts, it spins faster, just as an ice skater spins faster when pulling their arms inward. At the center of this collapsing cloud, pressure builds. Temperature rises. Eventually, the core becomes so hot, over 10 million degrees Celsius, that hydrogen atoms begin to fuse. Two hydrogen nuclei combine to form helium. In that moment, a star is born. Fusion releases energy. That energy pushes outward, balancing the inward pull of gravity. This balance is delicate. Gravity tries to collapse the star. Fusion tries to expand it. The star exists in a quiet equilibrium. Our sun is currently in this stage. It is about 4.6 billion years old and roughly halfway through its life. Stars spend most of their existence in this stable phase. It is called the main sequence. But not all stars are the same. Some are small, some are enormous. The smallest stars are called red dwarfs. They are faint and cool compared to the Sun, but they are incredibly efficient. Red dwarfs burn their fuel slowly and can live for trillions of years. In fact, the universe is not old enough for any red dwarf to have died yet. They are the quiet, long livers of the galaxy. Then there are stars like our Sun, medium-sized stars. They live about 10 billion years. When a Sun-like star runs low on hydrogen, its core contracts. The outer layers expand. The star becomes a red giant. It swells dramatically. If our Sun becomes a red giant, it may expand outward as far as the orbit of Earth. But do not worry. That will not happen for about 5 billion years. As the red giant phase continues, helium begins to fuse into carbon and oxygen. Eventually, the outer layers drift away into space. They form a glowing shell called a planetary nebula. At the center remains the core, a small, dense object called a white dwarf. White dwarfs are about the size of Earth, but contain roughly the mass of the Sun. They are incredibly dense. A teaspoon of white dwarf material would weigh tons. White dwarfs do not produce new energy. They slowly cool over billions of years, quietly fading. But massive stars have a very different fate. If a star begins its life with more than about 8 times the mass of the Sun, its story becomes dramatic. Massive stars burn their fuel quickly. They fuse heavier and heavier elements in their cores. Hydrogen to helium, helium to carbon, carbon to oxygen, oxygen to neon, neon to silicon, and eventually silicon to iron. But iron is different. Fusing iron does not release energy, it consumes it. Once iron builds up in the core, fusion stops producing outward pressure. Gravity wins. In less than a second, the core collapses inward. The outer layers crash down and rebound violently. The result is a supernova explosion. For a brief time, the star can shine brighter than an entire galaxy. Supernovae scatter heavy elements into space: gold, uranium, calcium. Many of the rare elements on Earth were created in these explosions. In the core that remains after a supernova, something extraordinary forms. If the remnant core is between about 1.4 and 3 times the mass of the Sun, it becomes a neutron star. Neutron stars are incredibly dense. Protons and electrons combine into neutrons. The result is a sphere about 20 kilometers across, but containing more mass than our Sun. 1 teaspoon of neutron star matter would weigh billions of tons. Some neutron stars spin rapidly, hundreds of times per second. They emit beams of radiation from their magnetic poles. If those beams sweep past Earth, we detect pulses. These are called pulsars, cosmic lighthouses spinning in the dark. If the collapsing core is even more massive, gravity overwhelms everything. Not even neutron pressure can resist it. The core collapses completely. Black holes are not cosmic monsters. They are natural outcomes of stellar evolution. In fact, the Milky Way may contain millions of stellar mass black holes. Most are invisible, quiet, orbiting within the galaxy. Stars are not isolated in their lives. Many form in clusters, groups of stars born from the same cloud. Some remain loosely associated, others drift apart over time. The Sun likely formed in such a cluster. Its stellar siblings are now scattered across the Milky Way. Somewhere in this galaxy, there are stars born from the same cloud as our Sun, perhaps with planets, perhaps with oceans, perhaps even with life. Let that thought settle gently. The Milky Way is filled with billions of stars, each with its own lifespan, each contributing to the chemical story of the galaxy. Birth, stability, transformation, recycling. The galaxy renews itself through stellar evolution. And as you listen, remember that the calcium in your bones was forged in a massive star. The iron in your blood was born in a supernova. You are connected to these cosmic processes, not metaphorically, physically, literally. The Milky Way is not only around you, it is within you. And just as stars move through their cycles, your own body moves through rhythms. Breathing in, breathing out, awake, and slowly drifting towards sleep. The life cycles of stars unfold over millions and billions of years. There is no rush. The universe does not hurry, and neither do you. Take a slow, gentle breath in, and let it drift out slowly. Now that we have explored how stars are born and how they fade, let us float outward again, into the vast spaces between them. The Milky Way is not just stars scattered in darkness, it is filled with clouds, soft, glowing clouds called nebulae. A nebula is simply a giant cloud of gas and dust drifting through space. Some are bright and colorful, others are dark and mysterious. There are different kinds of nebulae. Some are emission nebulae, where hot, young stars energize surrounding hydrogen gas, causing it to glow red. Others are reflection nebulae, which do not shine on their own, but gently reflect the light of nearby stars, often glowing blue. And then there are dark nebulae, dense clouds of dust that block starlight behind them. They appear as soft silhouettes against brighter regions of space. These clouds may seem empty, but they are the birthplace of future stars. Inside the Milky Way, thousands of nebulae drift quietly. One of the most famous is the Eagle Nebula, home to the Pillars of Creation. These towering columns of gas and dust stretch light years across. Within them, new stars are forming. Even destruction leads to creation. When massive stars explode as supernovae, their shock waves ripple through nearby gas clouds. These waves can compress the gas, triggering new star formation. The galaxy is constantly recycling itself. Old stars enrich the gas, new stars ignite, and the cycle continues. Beyond nebulae, the Milky Way contains beautiful gatherings of stars called star clusters. There are two main types. Open clusters are loose groups of young stars that formed together from the same cloud. They are often found in the spiral arms. These stars are like siblings, born at the same time, moving together through space. Over millions of years, they gradually drift apart. Then there are globular clusters. These are very different. Globular clusters are ancient. Some are nearly as old as the galaxy itself. They are tightly packed spheres containing hundreds of thousands of stars. Imagine a glowing ball of ancient suns bound closely by gravity. Globular clusters orbit the Milky Way far above and below the galactic disk. They belong to the galaxy's outer regions. And that brings us to something vast and invisible. Surrounding the entire Milky Way is a structure called the dark matter halo. Dark matter does not glow. It does not reflect light. It cannot be seen directly. But its gravity shapes the galaxy. When astronomers measured how fast stars move far from the galactic center, they noticed something surprising. The stars were moving too quickly. According to visible matter alone, they should have drifted away into space, but they did not. Something unseen was holding them in place. That unseen mass is dark matter. It forms a massive, spherical halo that extends far beyond the visible disk of the galaxy. In fact, most of the Milky Way's total mass is not made of stars or gas. It is dark matter. The luminous spiral you imagine is only a small part of a much larger structure. And yet, even with this hidden mass, the galaxy remains balanced. Gravity holds it together. Stars orbit calmly. Gas clouds drift. Clusters circle slowly through the halo. The Milky Way is not chaotic. It is structured, ordered, graceful. Now imagine drifting even farther out, looking back at the galaxy as a whole. A glowing spiral disk with a central bar of stars, soft arms winding outward, ancient clusters floating in the halo, all embedded in an invisible sphere of dark matter. It turns slowly in the dark, and inside it, on a small planet orbiting a quiet star, you are resting. The galaxy has been evolving for nearly 14 billion years. Nebulae forming stars, stars creating elements, clusters orbiting silently, dark matter shaping the structure. All of it happening long before humans ever looked up and wondered. And tonight, as the Milky Way continues its gentle rotation, you can let your thoughts drift. The clouds of gas glow softly. Ancient clusters shimmer. The hidden halo stretches outward into the cosmic night. Take a slow breath in and gently let it go. Now we travel backward, far backward, to a time before the Milky Way existed. Nearly 13.8 billion years ago, the universe itself began in the event we call the Big Bang. At first, there were no stars, no galaxies, no planets, only an expanding sea of energy and simple particles. Hydrogen and helium were the first elements to form. For hundreds of millions of years, the universe was dark. There were no stars yet to shine. Gravity, however, was already at work. Tiny fluctuations in density, regions just slightly denser than their surroundings, began pulling matter inward. These regions slowly grew. Clouds of hydrogen gas gathered together. As they became heavier, their gravity strengthened. Over time, these growing clumps became the first small galaxies. The early universe was not calm and orderly. It was busy. Young galaxies collided and merged frequently. They were much smaller than modern galaxies. Through these mergers, larger galaxies began to form. The Milky Way was born this way, not all at once, but gradually. Small proto-galaxies combined, gas flowed inward, dark matter halos merged. Over hundreds of millions of years, a larger structure began to take shape. At first, the Milky Way may have looked irregular, chaotic, misshapen. But as it grew more massive, gravity shaped it into a rotating disk. Rotation helped flatten it. Just as spinning pizza dough spreads outward, the galaxy's rotation formed a thin disk of stars and gas. The central region thickened into a bulge. Over time, spiral patterns emerged. The Milky Way did not grow alone. Even after its main structure formed, it continued to absorb smaller neighboring galaxies. Astronomers have found evidence of past mergers. Streams of stars stretch across the sky, remnants of dwarf galaxies that were pulled apart and absorbed. One such event is known as the Gaia-Enceladus merger, which likely happened around 10 billion years ago. A smaller galaxy collided with the early Milky Way. Its stars became part of the halo. Its motion altered the structure of our galaxy. Even today, the Milky Way is not finished growing. It is slowly merging with small dwarf galaxies nearby. Two of them, the Large and Small Magellanic Clouds, are visible from the southern hemisphere. They orbit our galaxy. Over time, they may be absorbed as well. Galaxies are not static objects. They evolve, they merge, they reshape themselves. The Milky Way today is far calmer than it was in its youth. Star formation has slowed. The most intense periods of starbirth are in the distant past. Yet it still forms a few new stars each year, quietly, steadily. And far in the future, another great transformation awaits. The Milky Way is moving toward the Andromeda Galaxy. They are drawn together by gravity. In about 4 billion years, they will begin to merge. Not in a sudden crash, but in a slow cosmic dance. Spiral arms will stretch. Stars will shift into new orbits. Gas clouds will compress and trigger new waves of star formation. Eventually, the two galaxies will become one larger galaxy. Astronomers sometimes call it Milkomeda. By that time, the Sun will be nearing the end of its life. Earth may no longer be habitable, but the galaxy itself will continue. Galaxies outlive stars. They outlive solar systems. They endure. The Milky Way has already survived billions of years of change. It has grown from small beginnings into a vast spiral structure over 100,000 light-years wide. And yet, compared to the scale of the universe, it is only one galaxy among trillions. Still, it is our home, born from simple hydrogen gas, shaped by gravity, built through mergers, enriched by generations of stars. And here you are, a conscious being on a small world inside this ancient structure. The atoms in your body were forged in stars that lived long before our sun. The galaxy's history flows through you. As you breathe in and gently out, remember this. You are resting inside a structure billions of years in the making. The Milky Way continues to evolve, slowly and patiently. There is no rush in cosmic time, only steady motion, only quiet gravity, only the gentle unfolding of the universe. Take a slow breath in and gently let it go. We have traveled into the past, to the birth of the Milky Way. Now let us drift forward, far into the future. The Milky Way today is mature. Its most intense era of star formation happened billions of years ago. Back then, gas was abundant. Stars formed more rapidly. The galaxy glowed brighter with young blue stars. But over time, gas has been used up. Some of it locked inside stars, some blown away by stellar winds and supernovae. Star formation continues, but more slowly now. Only about 1 to 3 new stars are born each year. In the distant future, that rate will decline even further. Eventually, the galaxy will run low on the cold gas needed to form new stars. When that happens, no more stellar nurseries will glow. No more brilliant blue giants will appear. The Milky Way will gradually become a quieter place. Its existing stars will continue their lives. Small red dwarfs will burn steadily for trillions of years. They are patient stars, long-lived, stable. But massive stars will have long since exploded. Even stars like our Sun will complete their life cycles. In about 5 billion years, the Sun will expand into a red giant. Its outer layers will swell outward. Mercury and Venus may be consumed. Earth's surface will become too hot for oceans. But even that is only a chapter in a much longer story. After shedding its outer layers, the Sun will leave behind a white dwarf, a small, dense ember cooling slowly in the dark. Over billions more years, that white dwarf will fade, cooling further, becoming dimmer. The galaxy too will change. In about 4 billion years, the Milky Way and Andromeda will begin their great merger. At first, tidal forces will stretch both galaxies. Spiral arms will distort. Long streams of stars will arc into space. But direct star collisions will be extremely rare. Space between stars is vast. Instead, stars will settle into new orbits within a larger, combined galaxy. The final shape may not be spiral at all. It could become an elliptical galaxy, a vast glowing sphere of aging stars. New waves of star formation may briefly ignite during the merger as gas clouds collide and compress. But eventually, the gas will again be used up. Over time, the galaxy will become dominated by older, redder stars, quieter, calmer. And far beyond even that future, something deeper is unfolding. The universe itself is expanding. Not just expanding, accelerating. Distant galaxies are moving away from us faster and faster. In tens of billions of years, most other galaxies will move beyond our observable horizon. Light from them will no longer reach us. The merged Milky Way Andromeda Galaxy may become the only visible galaxy in the night sky. Future astronomers, if any exist, may see only their own galaxy and dark emptiness beyond. The cosmic web will stretch thinner. The universe will grow darker. But this is not something to fear. It is simply the long arc of cosmic evolution. Stars will continue shining for trillions of years. Red dwarfs will glow softly. White dwarfs will cool slowly. Neutron stars will spin quietly. Black holes will drift unseen. And eventually, in unimaginable stretches of time, even star formation everywhere will cease. The universe will enter what some call the stelliferous era's end. But that is so far away that it is difficult even to comprehend. For now, the Milky Way is vibrant, alive with stars, alive with motion, alive with light. And you are here during one of its luminous chapters, a time when spiral arms still shine, when nebulae still glow, when stars are still being born. The future of the Milky Way is long and gradual. There are no sudden endings, only transitions, only transformations. Gravity continues its gentle work. Time continues its steady flow. And as the galaxy evolves over billions of years, you can rest in this moment. A small being inside a vast structure that has endured since near the beginning of time. The Milky Way will change. Stars will fade. Galaxies will merge. The universe will expand. But tonight, the spiral arms still turn above you, and your breath moves softly in and out. Take a slow breath in and gently let it go. Tonight, we turn from the distant future back to something closer. How did we learn all of this? How did humans, standing on a small planet, figure out the structure of a galaxy 100,000 light-years wide? For most of human history, people believed the Milky Way was simply a glowing band in the sky. The ancient Greek philosopher Democritus suggested it might be made of distant stars. But it was not until 1609 that someone truly tested that idea. When Galileo Galilei pointed one of the first telescopes toward the Milky Way, he saw something astonishing. The faint mist resolved into countless tiny stars. The Milky Way was not a cloud. It was a sea of suns. That discovery was only the beginning. For centuries afterward, astronomers tried to understand how these stars were arranged. In the 18th century, William Herschel attempted to map the galaxy by counting stars in different directions. He imagined the Milky Way as a flattened disk. He was partly correct, but there was a problem: dust. Interstellar dust blocks visible light. When Herschel looked toward the center, dust prevented him from seeing very far. He concluded that the Sun was near the center of the galaxy. It was a reasonable guess, but it was wrong. In the early 20th century, a new breakthrough came. Astronomer Harlow Shapley studied globular clusters. He noticed that these ancient clusters were not evenly distributed around us. They were concentrated in one direction: Sagittarius. By measuring distances to these clusters, Shapley realized something profound. The center of the Milky Way was not near the Sun. We were off to the side. For the first time, humanity understood that we are not central. We are suburban residents in a vast cosmic city. Later, radio astronomy changed everything again. Radio waves can pass through dust. In the mid-20th century, astronomers mapped hydrogen gas across the galaxy using radio telescopes. This allowed them to trace the spiral arms. Piece by piece, a clearer picture emerged. The Milky Way was a barred spiral galaxy, rotating, layered, structured. More recently, space telescopes and satellites have refined our understanding. The Gaia spacecraft, launched in 2013, has mapped the precise positions and motions of over 1 billion stars. From this data, astronomers can reconstruct the galaxy's history. They can see where stars are moving, where streams of past mergers stretch, where the spiral arms ripple. Even the black hole at the center was confirmed by tracking the orbits of nearby stars. Their rapid motion revealed the presence of something massive and invisible. In 2022, the first direct image of Sagittarius A star was released, a glowing ring of light surrounding darkness, proof of something once purely theoretical. And yet, even with all this knowledge, we have never seen a full photograph of the Milky Way from the outside. Every beautiful spiral image you see is of another galaxy. We cannot step outside our own. We must reconstruct it from within. Like trying to map a forest while standing among the trees. This makes the achievement even more remarkable. From a small world orbiting one ordinary star, humans have pieced together the structure of a galaxy that spans 100,000 light-years. We did it with patience, with mathematics, with light gathered from distant stars, and with curiosity, the desire to understand what lies beyond. Tonight, as you rest, remember this gentle truth. Everything we know about the Milky Way was discovered by small beings looking up at the sky. No faster than light travel, no grand cosmic journeys, only observation, careful measurement, and imagination guided by evidence. We live inside something vast, and yet we have learned so much about it. The galaxy continues turning, stars continue shining, and human curiosity continues reaching outward. Take a slow breath in, and gently let it drift out. Now let us become more personal. We've explored the structure of the Milky Way, its center, its spiral arms, its halo. But where exactly are you inside this vast system? Imagine the galaxy as a giant rotating disk about 100,000 light-years across. At the center lies the bright bulge and the supermassive black hole. Spiral arms wind outward like soft cosmic ribbons. Now picture a point not at the center but partway out, about halfway between the core and the outer edge. That is where we are. Our Sun sits roughly 27,000 light-years from the galactic center. We are located in a small structure called the Orion Arm, sometimes called the Orion Spur. It is not one of the main spiral arms. It is more like a smaller bridge between two larger arms, the Perseus Arm and the Sagittarius Arm. In cosmic terms, we live in a quiet neighborhood, not in the crowded city center, not in the sparse outskirts, just comfortably in between. This location may have been fortunate. Near the galactic center, stars are densely packed. Supernovae occur more frequently. Radiation levels are higher. Closer to the outer edge, there are fewer heavy elements available to build rocky planets. Our position provides balance. Enough heavy elements from earlier generations of stars to build Earth and life, but far enough from intense radiation to remain stable. Astronomers sometimes refer to this idea as the galactic habitable zone, a region within a galaxy where conditions may be favorable for life. We appear to be inside it. Now imagine standing outside on a clear, dark night. When you see the Milky Way stretching overhead like a pale river of light, what you are really seeing is the disk of our galaxy from inside. When you look along the band, you are looking through the dense plane where most stars are located. That is why it appears brighter. When you look above or below that band, you are looking out of the disk, into thinner regions of space. The night sky becomes darker there. If we could somehow travel far above the galaxy and look back down, we would see our sun as just one small star among billions. Its light would not stand out. Earth would be invisible. And yet, here, from our perspective, the sky feels immense. Scale depends on where you stand. Our solar system orbits the galactic center at about 828,000 kilometers per hour. But because everything around us is moving at nearly the same speed, we do not feel that motion. It is smooth, steady, like riding in a perfectly quiet train. The Sun completes one orbit every 225 to 250 million years. Since Earth formed, it has circled the galaxy about 20 times. And during your lifetime, the solar system moves millions of kilometers around the Milky Way. Yet the night sky changes only slowly. Constellations shift gradually over tens of thousands of years. Stars drift in their own individual motions, each orbiting the center in slightly different paths. The galaxy is dynamic, alive with motion, but patient. Everything happens on timescales so vast that it feels almost still. Now imagine zooming outward one more time, from Earth to the solar system, from the solar system to the Orion Arm, from the Orion Arm to the full spiral galaxy. You are a tiny part of a structure 100,000 light-years wide. Yet your existence is made possible by that very structure. The heavy elements in your body were forged by previous generations of stars inside this galaxy. The Sun was born from a cloud enriched by ancient supernovae. Earth formed from leftover debris in that spinning disk of gas and dust. You are not separate from your galactic surroundings. You are an expression of them. The Milky Way is not just above you, it is around you and within you. As you breathe in and slowly out, imagine the spiral arms turning gently. Imagine the Orion Arm quietly carrying our Sun through space. You are riding a planet, orbiting a star, orbited a galactic center, within a universe still expanding. And yet this moment is calm. Take a slow breath in and gently let it go. Tonight we drift into something subtle. Not the brightness of stars, not the drama of supernovae, but the quiet space between them. When we imagine space, we often think of silence, complete silence, and in many ways that is true. Sound, as we know it, requires air or another medium to travel. On Earth, sound moves through air as vibrations. In water, it moves through liquid. But the space between stars is almost empty. It contains only a few atoms per cubic centimeter, far less dense than the best vacuum we can create on Earth. If you were floating between stars, you would not hear explosions. You would not hear wind. You would not hear anything at all. Supernovae would unfold in brilliant light, but in perfect silence. And yet, the galaxy is not entirely quiet. While sound cannot travel through empty space, vibrations still exist. Gas clouds ripple. Magnetic fields twist and flex. Stars oscillate internally. These movements create pressure waves within the gas of nebulae and within stars themselves. Astronomers can detect these oscillations using sensitive instruments. By studying tiny variations in brightness, they can listen to stars. This field is called astroseismology. Like seismology on Earth, which studies earthquakes to understand our planet's interior, astroseismology studies stellar vibrations to learn about the inside of stars. Stars ring, not audibly, but mathematically. They expand and contract slightly, resonating in complex patterns. Each star has its own subtle rhythm. In a sense, the Milky Way is filled with silent music. Now imagine drifting through a nebula, hydrogen gas stretching across light years. Even there, the density is extremely low. But shock waves from supernovae can ripple through these clouds at hundreds of kilometers per second. The waves compress the gas, triggering new stars. Though we would hear nothing, the galaxy is dynamic, alive with motion. Even the black hole at the center creates waves. When matter spirals inward, it heats up, emits radiation, and in rare cases, black holes merging create gravitational waves. These waves are not sound. They are ripples in the fabric of space-time itself. In 2015, scientists detected gravitational waves for the first time. The signal came from two black holes merging far beyond our galaxy. The event happened over 1 billion years ago, yet the ripple reached Earth and gently stretched and squeezed space by a fraction of the width of a proton. Even in silence, the universe communicates. Now imagine standing on Earth under a dark sky. You hear crickets, wind in trees, perhaps distant ocean waves. All of these sounds are local, earthly. Above you, the Milky Way glows silently. No cosmic roar, no galactic hum, just light traveling across vast distances to reach your eyes. It is comforting in a way. The galaxy's most dramatic events happen without noise. Even immense explosions are quiet from afar. The Milky Way is not chaotic and loud. It is serene, vast, patient. And in that silence, there is space for thought, for curiosity, for wonder. Now imagine floating once more between the stars. No up, no down, no sound. Just distant points of light. The nearest star beyond the Sun would still be more than 4 light-years away. The emptiness is not frightening. It is spacious, like an open ocean at night. Calm, boundless. The silence of space reminds us how precious sound is here on Earth. The rhythm of breath, the soft beat of a heart. These are small sounds in a very large universe. As you breathe in and slowly out, notice the gentle sound of air moving through your lungs. That simple sound is more immediate than any galactic event. The Milky Way turns quietly above you. Stars burn without noise. Nebulae drift in silence. Black holes wait without sound. And you rest in the small pocket of atmosphere that makes sound possible. Take a slow breath in and gently let it go. Tonight, we explore one of the most comforting ideas the Milky Way offers. We are not alone in having planets. For most of human history, we did not know whether other stars had worlds orbiting them. It was only in 1992 that astronomers confirmed the first planets beyond our solar system. These are called exoplanets. Since then, thousands have been discovered, and now we understand something extraordinary. Planets are common, very common. Most stars in the Milky Way likely host at least one planet. Some host many. If there are between 100 and 400 billion stars in our galaxy, there may be hundreds of billions of planets. Imagine that number for a moment. Hundreds of billions of worlds. Some are gas giants, larger than Jupiter. Some are rocky worlds, similar in size to Earth. Some orbit very close to their stars. Others drift far out in cold darkness. Astronomers have discovered a remarkable variety of planets. There are hot Jupiters, massive gas planets orbiting so close to their stars that their atmospheres glow with heat. There are super-Earths, rocky planets larger than ours but smaller than Neptune. There are even rogue planets, worlds not bound to any star at all. These wander the galaxy alone, traveling through interstellar space. And then there are planets in what scientists call the habitable zone. This is the region around a star where temperatures might allow liquid water to exist on a planet's surface. Water is essential for life as we know it. Our Earth lies within the Sun's habitable zone, but many other stars also have planets in this gentle region. Some orbit small red dwarfs. Others orbit stars similar to the Sun. In recent years, astronomers have detected water vapor and even organic molecules in the atmospheres of distant planets. The James Webb Space Telescope has begun studying these worlds in greater detail. By analyzing starlight passing through a planet's atmosphere, scientists can identify the chemical fingerprints of gases: oxygen, methane, carbon dioxide. Clues, hints, possibilities. So far, we have not found confirmed life beyond Earth, but the ingredients appear to be widespread. The Milky Way is vast. Even if life is rare, billions of planets offer many opportunities. Some stars in our galaxy are older than the Sun. Their planets may have had billions of extra years for life to evolve. Others are younger, with new worlds just forming. The timeline of the galaxy is wide enough for countless stories. Now imagine looking up at the night sky again. Every star you see may host its own system of planets. Some planets may have oceans, some may have thick clouds, some may be frozen solid, and somewhere, on some small rocky world orbiting a quiet star, there may be another being looking up at their sky, wondering the same question. Are we alone? The Milky Way does not answer directly, but it provides scale. Scale that expands possibility. The distances between stars are enormous. Travel between them is difficult with our current technology. The nearest star system, Alpha Centauri, is over 4 light-years away. Even traveling at the speed of our fastest spacecraft, it would take tens of thousands of years to arrive. And yet, signals travel at the speed of light. Scientists have searched for radio signals from other civilizations. This effort is known as SETI, the Search for Extraterrestrial Intelligence. So far, we have detected no confirmed signals, but the search continues, quietly, patiently. The Milky Way is not small. It spans 100,000 light-years, and even within that vast space, we have explored only a tiny fraction. Like standing on one shore of a great ocean and wondering about the lands beyond. Tonight, as you breathe slowly in and gently out, let this thought settle softly. You are on one world among billions, orbiting one star among hundreds of billions, inside one galaxy among trillions. The possibility of other worlds does not diminish you. It connects you. It reminds you that you are part of a grand story, written in hydrogen and gravity. The Milky Way holds countless planets, some barren, some beautiful, some perhaps alive. And here, on Earth, you rest on one small sphere, spinning gently under the light of a quiet star. The universe is a vast, expanding continuum of space, time, matter, and energy. Its observable portion stretches approximately 93 billion light-years in diameter, though its full extent may be far greater. Within this immense structure, galaxies drift apart as space itself expands. a process first observed through the redshift of distant galaxies. This steady expansion gives the cosmos a gentle, unhurried rhythm, measured not in minutes or years, but in billions of years. A light year, the distance light travels in 1 year, equals about 9.46 trillion kilometers. Even traveling at the speed of light, a beam would take over 4 years to reach the nearest star beyond our Sun, Proxima Centauri. Such distances illustrate the serene spaciousness of the cosmos, where objects are separated by vast expanses of near-perfect vacuum. Galaxies are the fundamental building blocks of the large-scale universe. Each galaxy contains millions to trillions of stars, along with gas, dust, and dark matter. Our home galaxy, the Milky Way, contains an estimated 100 to 400 billion stars. From Earth's surface on a clear night, the Milky Way appears as a soft band of diffuse light, a reminder that we reside within a rotating island of stars. Between galaxies lies intergalactic space, where the density of matter is extremely low, often just a few atoms per cubic meter. This quiet emptiness dominates the cosmos. Even within galaxies, stars are separated by such great distances that direct collisions are exceedingly rare. The universe, despite containing unimaginable quantities of matter, is primarily empty space. Nebulae, vast clouds of gas and dust, drift through galaxies like luminous veils. Some nebulae mark the birthplaces of stars, where gravity slowly gathers material into dense regions that eventually ignite nuclear fusion. Others are remnants of stars that have gently shed their outer layers or ended their lives in supernova explosions. Over millions of years, these clouds evolve in silence, reshaped by gravity and radiation. Time in space unfolds slowly. Stars live for millions or billions of years. Galaxies merge over spans far exceeding human history. Even the cosmic microwave background radiation, the faint afterglow of the early universe, has been traveling through space for approximately 13.8 billion years, offering a quiet echo of cosmic beginnings. Gravity provides structure to this calm vastness. It binds stars into galaxies and galaxies into clusters. Yet gravity also operates gradually, guiding celestial bodies along predictable paths. Planets orbit stars in steady ellipses. Moons circle planets in dependable cycles. These motions create cosmic stability, a celestial choreography governed by precise physical laws. Silence, in the conventional sense, prevails throughout most of space. Because sound requires a medium through which to travel, the near vacuum of interstellar space carries no audible waves. While electromagnetic radiation, such as visible light and radio waves, moves freely across the void, the universe itself remains acoustically still. Dark matter and dark energy, though invisible, shape the structure and expansion of the cosmos. Dark matter provides gravitational scaffolding that holds galaxies together, while dark energy appears to accelerate the expansion of space. Together, these unseen components comprise most of the universe's total energy content, quietly influencing its evolution. From the perspective of Earth, space may seem distant and abstract. Yet every atom in the human body was forged in ancient stars. The carbon in cells, the oxygen in the air, and the iron in blood originated in stellar furnaces long before the solar system formed. In this sense, humanity is intimately connected to the calm processes of cosmic history. The observable universe contains billions of galaxies, each separated by immense distances, each following the same physical principles. Light travels steadily through the vacuum. Gravity shapes matter. Time advances without haste. Across scales both immense and minute, the cosmos remains governed by consistency and balance. In contemplating these vast and tranquil structures, one may sense the slow, enduring nature of cosmic time. Stars shine quietly. Galaxies drift imperceptibly. Space expands steadily. Within this grand stillness, the universe unfolds at a pace far beyond the urgency of daily life, a reminder that existence itself moves with profound patience. Stars are luminous spheres of plasma, held together by gravity and powered by nuclear fusion. Their lives unfold over immense timescales, often lasting billions of years. In this quiet endurance, stars represent some of the most stable and persistent structures in the universe. A star begins its existence within a molecular cloud, a cold and diffuse region of gas and dust drifting through a galaxy. Over time, gravity gently draws particles together. As the cloud contracts, its core grows denser and warmer. When temperatures reach several million degrees, hydrogen atoms begin to fuse into helium, releasing energy. This marks the birth of a star. For most of its life, a star remains in what astronomers call the main sequence. During this long stage, the outward pressure from nuclear fusion balances the inward pull of gravity. This equilibrium can persist for billions of years. Our Sun, for example, is approximately 4.6 billion years old and is expected to remain stable for another 5 billion years. The light emitted by a star travels vast distances across space. It moves silently through the vacuum, illuminating planets and nebulae. The warmth felt on Earth from sunlight began its journey at the Sun's core thousands of years ago, before finally reaching the surface and traveling the final 8 minutes through space to Earth. Stars vary in size, temperature, and color. Smaller stars, known as red dwarfs, burn their fuel slowly and can shine for trillions of years, far longer than the current age of the universe. Larger stars live shorter but more luminous lives. Despite these differences, all stars follow predictable physical laws governed by gravity and thermodynamics. As a star exhausts the hydrogen in its core, it gradually changes. Medium-sized stars expand into red giants, gently shedding their outer layers into space. The remaining core cools over time into a white dwarf, a dense, faint remnant that slowly radiates its stored heat away over billions of years. More massive stars may end in supernova explosions, dispersing heavy elements into space. Yet, even these dramatic events unfold according to well-understood processes. From the remnants of such explosions, new stars and planetary systems may eventually form, continuing a calm, cosmic cycle of transformation. The night sky offers a view into stellar history. Because light takes time to travel, observing distant stars is equivalent to looking into the past. Some stars visible to the unaided eye may no longer exist in their original form, yet their light continues its steady journey toward Earth. Constellations, patterns formed by stars as seen from Earth, are products of perspective. Though they appear grouped together, the stars within a constellation may be separated by vast distances in three-dimensional space. Their apparent closeness is a quiet illusion created by our viewpoint within the galaxy. The steady glow of stars has guided navigation, calendars, and scientific discovery for millennia. Their slow and predictable motions across the sky reflect Earth's rotation and orbit, creating reliable cycles of night and season. In the broader context of the universe, stars represent ongoing processes of balance. Gravity compresses, fusion releases energy, equilibrium sustains light. Across incomprehensible spans of time, these luminous spheres shine calmly, marking the passage of cosmic ages with consistent radiance. Planets and moons move through space in steady, predictable paths shaped by gravity. Their motion is neither hurried nor chaotic, but governed by precise physical laws that have remained consistent for billions of years. This continuous movement forms a quiet celestial dance, unfolding at a scale far beyond ordinary human perception. A planet orbits a star due to the balance between gravitational attraction and forward motion. Gravity pulls the planet inward, while its velocity carries it forward, creating an elliptical path. This principle, described mathematically in the 17th century, applies universally, from small rocky planets to distant gas giants. Within our solar system, 8 major planets orbit the Sun. Each follows a distinct path, taking varying lengths of time to complete a full revolution. Mercury completes an orbit in just 88 Earth days, while Neptune requires approximately 165 Earth years. Despite these differences, the system remains stable over immense periods of time. Moons orbit planets through the same gravitational principles. Earth's moon, for example, completes one orbit approximately every 27.3 days. Its steady motion produces the familiar lunar phases, as sunlight illuminates changing portions of its surface. These phases repeat in a regular cycle, creating one of the most ancient and observable astronomical rhythms. Tidal forces arise from gravitational interactions between celestial bodies. The gravitational pull of the moon affects Earth's oceans, generating tides that rise and fall with dependable regularity. This interaction also gradually slows Earth's rotation over geological timescales, demonstrating that even subtle gravitational effects accumulate over millions of years. Gas giants, such as Jupiter and Saturn, possess extensive systems of moons. Jupiter alone has more than 90 confirmed natural satellites. These moons range from small, irregular rocks to large, spherical worlds with subsurface oceans. Each follows its own orbital period, forming intricate gravitational relationships that maintain long-term stability. Saturn's rings offer another example of ordered motion. Composed primarily of ice and rock particles, the rings consist of countless fragments orbiting in thin, flat bands. Each particle follows its own path around the planet, yet collectively, they create a structured and harmonious system. Orbital resonance occurs when 2 or more moons exert regular gravitational influences on one another. This can lead to synchronized patterns in their orbits. Such resonances help maintain order within complex planetary systems and prevent instability. Rotation adds another dimension to planetary motion. While orbiting their star, planets also rotate on their axes. Earth completes one rotation approximately every 24 hours, creating the cycle of day and night. Other planets rotate more slowly or rapidly. Jupiter, for example, rotates in just under 10 hours, despite its enormous size. Seasons result from axial tilt rather than distance from the Sun. Earth's axis is tilted by about 23.5 degrees, causing different regions to receive varying amounts of sunlight throughout the year. This tilt produces predictable seasonal changes, another steady rhythm in the broader dance of celestial mechanics. Beyond our solar system, thousands of exoplanets orbit distant stars. Observations suggest that planetary systems are common throughout the galaxy. Though each system may vary in structure, the same gravitational principles govern their motion. Over billions of years, planetary orbits can shift gradually due to gravitational interactions. Yet these changes unfold slowly, measured across vast stretches of time. For observers on Earth, the sky appears stable, with planets tracing consistent paths against the background of distant stars. The motion of planets and moons illustrates balance in action. Gravity provides structure. Motion provides continuity. Together, they create a system of enduring cycles, rotations, revolutions, phases, tides, and seasons. In contemplating this slow and graceful movement, one encounters a universe governed not by haste, but by equilibrium. Planets continue their orbits without interruption. Moons circle their worlds in patient repetition. Across the darkness of space, the celestial dance proceeds quietly, sustained by forces that have shaped the cosmos since its earliest ages. Black holes are regions of spacetime where gravity becomes so strong that nothing, not even light, can escape once it passes a boundary known as the event horizon. Despite their dramatic reputation, black holes are not cosmic vacuum cleaners. They do not roam the universe, consuming everything in their path. Instead, they obey the same gravitational laws as other massive objects, influencing their surroundings in predictable ways. A black hole forms when a massive star exhausts its nuclear fuel and its core collapses under gravity. If the remaining mass is sufficient, no known force can prevent continued collapse. The matter compresses into an extremely dense state, creating a gravitational field of extraordinary strength. This transformation occurs according to well-understood physical principles. The event horizon marks the boundary beyond which escape is impossible. It is not a solid surface, but a mathematical limit in spacetime. Outside this boundary, objects can orbit safely if they maintain sufficient distance and velocity. Many stars and gas clouds orbit black holes without falling inward, demonstrating that these objects can exist within stable systems. At the center of most large galaxies resides a supermassive black hole. In the Milky Way, this object is known as Sagittarius A star. Its mass is approximately 4 million times that of the Sun. Yet it occupies a region smaller than the orbit of Mercury. Despite its immense mass, it remains distant from Earth, about 26,000 light-years away, and exerts no disruptive influence on our solar system. Matter drawn toward a black hole often forms an accretion disk, a rotating structure of gas and dust spiraling inward. As particles within the disk collide, they heat up and emit radiation. This process can produce bright emissions, detectable across vast distances. The glow of an accretion disk, rather than the black hole itself, is often what astronomers observe. Some black holes generate jets, narrow streams of high-energy particles extending far into space. These jets are guided by magnetic fields and can stretch thousands of light-years. Even so, their formation follows consistent physical mechanisms tied to rotation and magnetic interactions. Black holes vary in size. Stellar mass black holes form from individual stars. Intermediate mass black holes are less common and still under active study. Supermassive black holes anchor galactic centers. Regardless of scale, each is defined primarily by mass, spin, and charge, simple parameters that fully describe their properties. Time behaves differently near a black hole due to gravitational time dilation. Clocks closer to the event horizon tick more slowly relative to distant observers. This phenomenon arises from general relativity and has been experimentally confirmed in weaker gravitational fields. Near a black hole, the effect becomes extreme, but remains consistent with physical law. Despite their name, black holes are not entirely black. Theoretical predictions suggest they emit extremely faint radiation, known as Hawking radiation, caused by quantum effects near the event horizon. Over inconceivably long timescales, this radiation may cause black holes to lose mass and eventually evaporate. Gravitational lensing provides another observable effect. The intense gravity of a black hole can bend light from objects behind it, distorting their apparent shape. This bending of spacetime is not chaotic, but mathematically predictable, offering further confirmation of gravitational theory. In 2019, astronomers released the first direct image of a black hole's shadow, captured by the Event Horizon Telescope. The image revealed a bright ring of light surrounding a dark center, visual evidence of matter orbiting near the event horizon. This observation reinforced decades of theoretical work. Though they represent extremes of gravity and density, black holes contribute to cosmic structure. They influence star formation in galaxies and help regulate galactic evolution. Rather than symbols of destruction, they are integral components of large-scale cosmic balance. Within the immense quiet of space, black holes remain stable, defined by precise equations and governed by universal laws. Their gravity shapes motion. Their presence anchors galaxies. Their mysteries inspire study, yet their behavior remains orderly. In contemplating black holes, one encounters not chaos, but depth. Regions where space-time curves profoundly, where gravity reaches its limit, and where the universe reveals its most subtle structures. Even here, at the edge of physical extremes, the cosmos continues its slow and steady unfolding. The universe is not static. Since its earliest moments, space itself has been expanding. This expansion does not resemble an explosion moving outward into emptiness. Rather, it is the gradual stretching of space in all directions. Galaxies are not flying through space away from a central point. Instead, the space between galaxies slowly increases, carrying them farther apart over time. Observations of distant galaxies reveal that their light is shifted toward longer, redder wavelengths, a phenomenon known as redshift. This effect occurs because as space expands, the light traveling through it also stretches. The greater the distance to a galaxy, the more pronounced its redshift tends to be. This relationship provides strong evidence that the universe has been expanding for billions of years. The rate of expansion is described by the Hubble constant, named after the astronomer Edwin Hubble, who first confirmed the systematic recession of galaxies in the 1920s. Modern measurements continue to refine this value. Although the precise number is still under careful study, the overall conclusion remains consistent. The universe is expanding. The expansion began approximately 13.8 billion years ago, during an early phase of rapid growth that set the foundation for cosmic structure. In its first moments, the universe was extremely hot and dense. As it expanded, it cooled. Over time, particles combined to form atoms, and gravity gradually gathered matter into stars and galaxies. One of the most important pieces of evidence for this early period is the cosmic microwave background radiation. This faint glow fills all of space and represents light released when the universe became transparent, roughly 380,000 years after its beginning. Today, this radiation is observed as a nearly uniform background at a temperature of about 2.7 degrees above absolute zero. Its smooth distribution reflects the remarkable uniformity of the early cosmos. Though expansion increases the distance between galaxies, it does not affect gravitationally bound systems such as galaxies themselves, solar systems, or planets. Within these systems, gravity remains strong enough to counteract the stretching of space. The Earth does not drift away from the Sun due to cosmic expansion, and stars within galaxies remain gravitationally connected. In recent decades, observations have revealed that expansion is not merely continuing, it is accelerating. This acceleration is attributed to a phenomenon known as dark energy, an unseen component that appears to permeate space. Dark energy constitutes the majority of the universe's total energy content and influences the large-scale behavior of cosmic expansion. Despite its vast scale, the expansion of the universe is gentle. On human timescales, it is imperceptible. Galaxies drift apart over millions and billions of years. The night sky, as seen from Earth, appears largely unchanged over a lifetime. Yet across cosmic history, distances grow steadily, shaping the evolving structure of the universe. Deep-field astronomical images reveal thousands of distant galaxies within small patches of sky. Many of these galaxies are observed as they were billions of years ago, because their light has taken immense time to reach Earth. In this way, observing the distant universe is equivalent to looking backward through time. As expansion continues, distant galaxies will gradually move beyond the observable horizon. their light will become so stretched and faint that it will no longer reach us. However, this process unfolds across unimaginably long durations. The expansion of the universe illustrates a principle of cosmic calm. Even at the largest scale imaginable, change occurs gradually. Space stretches quietly. Galaxies drift patiently. Light travels steadily across widening distances. There is no central edge from which the universe expands, and no boundary into which it moves. Every region of space experiences expansion similarly. From any galaxy's perspective, others appear to recede. This symmetry reinforces the idea that the universe has no preferred center. In contemplating cosmic expansion, one encounters an image of slow transformation. The universe does not rush. It unfolds over billions of years, guided by consistent physical laws. The distances between galaxies grow. The background radiation cools. Structures evolve gently under gravity's influence. Within this immense and measured process, the cosmos continues its quiet journey outward, expanding not with noise or turbulence, but with steady persistence across the vast silence of space. Galaxies are vast systems, composed of stars, gas, dust, dark matter, and gravitational structure. They represent some of the largest organized formations in the universe. Though immense in scale, galaxies evolve slowly, changing shape and structure across billions of years. Astronomers classify galaxies into several primary types. Spiral galaxies, such as the Milky Way, display curved arms that extend outward from a central bulge. These arms contain young stars, nebulae, and interstellar clouds. Elliptical galaxies appear smoother and more rounded, often containing older stars and less interstellar gas. Irregular galaxies lack defined structure, shaped by gravitational interactions or past collisions. The Milky Way is a barred spiral galaxy, spanning approximately 100,000 light-years in diameter. It contains hundreds of billions of stars, orbiting a central region. Our solar system resides in one of its spiral arms, about 27,000 light-years from the galactic center. From Earth, the Milky Way appears as a faint band of light across the night sky, a gentle reminder of our place within a much larger system. Stars within galaxies orbit their centers due to gravity. These motions are not random, but follow stable paths determined by mass distribution. Dark matter, though invisible, plays a significant role in maintaining galactic structure. Observations show that galaxies rotate in ways that cannot be explained by visible matter alone, suggesting that unseen mass surrounds them like an extended halo. Galaxies are not isolated. They often exist in groups or clusters, bound together by gravity. The Milky Way belongs to a small assembly known as the local group, which includes the Andromeda Galaxy and dozens of smaller galaxies. Over immense timescales, galaxies within such groups may gradually move toward one another. The Andromeda Galaxy, located about 2.5 million light-years away, is slowly approaching the Milky Way. This motion, however, unfolds over billions of years. If the two galaxies eventually merge, the event will occur gradually, with stars passing one another across vast distances. Direct stellar collisions would remain extremely rare. Deep field observations of the universe reveal that even tiny patches of sky contain thousands of galaxies. Each faint point of light represents a system potentially containing billions of stars. Many of these galaxies are observed as they existed long ago, their light traveling immense distances to reach Earth. Galaxies also contain vast regions of interstellar space. Though populated by stars, most of a galaxy's volume consists of empty or nearly empty space. The distances between stars are so great that even within a galaxy, space remains largely silent and open. Over time, galaxies evolve. Star formation gradually consumes available gas. Supernovae enrich interstellar material with heavier elements. Gravitational interactions reshape structure. Yet, these processes occur slowly, measured in millions or billions of years. In galaxy clusters, gravitational forces create larger-scale patterns. Galaxies orbit cluster centers, sometimes linked by faint streams of gas. Hot plasma fills the space between them, emitting X-rays detectable by space observatories. Even these energetic environments maintain long-term equilibrium governed by gravity. When viewed collectively, galaxies form a vast cosmic web. This large-scale structure resembles filaments and nodes, where clusters connect across enormous distances. Between these filaments lie enormous voids, regions containing few galaxies. The overall pattern extends across hundreds of millions of light-years. Light from distant galaxies grows fainter as it travels through expanding space. Some of the most distant galaxies appear as soft, reddish smudges in telescope images. Their light began its journey when the universe was young, offering insight into early cosmic history. Despite their size and complexity, galaxies maintain balance. Gravity binds them together. Rotation stabilizes structure. Matter cycles through generations of stars. Across the observable universe, billions of galaxies drift quietly within expanding space. In contemplating distant galaxies, one encounters scale beyond ordinary experience. Each luminous spiral or smooth ellipse represents a vast community of stars, evolving gently over cosmic time. Their glow reaches Earth after traveling millions or billions of years, carrying with it a record of patient transformation. The gentle radiance of galaxies reminds us that the universe unfolds gradually. Stars orbit, gas drifts, clusters rotate. Across incomprehensible distances, the cosmos maintains its quiet architecture, structured, expansive, and enduring.